Welcome, class. It's Dr. Jim Rose again, and what we're going to do today is take a look at Activity 19. This is the activity for Observation 3 in Stars and Galaxies. And in this observation, basically what we're going to be doing is looking at several stars and recording the data given by the program. Such data as the Bayer designation, or the distance from the Sun, its luminosity, its position, and so on. The stars that we're going to each look at are Alpha Centauri, Betelgeuse, Deneb, Barnard's star. Okay, and then we're going to do some luminosity calculations, and we're going to do a little bit of how long it would take to count the stars in the Milky Way galaxy. So, excuse me, that's what we're up to. This presentation is going to be a little bit shorter than the last one because basically it's just repetition. We're going to be doing the same thing over and over again for each of these stars. So I will give you the example for Alpha Centauri, and from there you're on your own. I will then come back and we'll talk about the luminosity calculations and the calculation for counting stars. So let us share. Here's my starry night. All right, so we are now sharing. We're now sharing Starry Night. The first thing that you have to do is to begin to set up the system. And what you're going to do is you're going to go to Sunset. And that's part 2, basically setting it up. So you come over here to the drop-down menu for time and date on the control panel here. Drop down to Sunset, and it switched there fairly quickly. The next thing that they tell you to do is look west. Now remember, you can always view and go to west, or you can just hit the W button, which is what I'm going to do. Hit the W, then hit the space bar, and you'll get there very quickly. So now here we are, we're looking west, it's at sunset. Looks like the sun is over here a little bit, and it's at sunset. If we speed this up, we're supposed to speed up the system to 300, so let's speed the system up to 300. And we're going to let it run until it turns dark, and we can start to see the stars. Okay, so now we definitely can see the stars. It's still dusk, but we can definitely see the stars. We have a real bright star right here. That's Arcturus. There's a red star here, Antares. And here's another I guess is the name of that one. Those are 3 of the ones that pop out on my screen. You may also notice that there's a star here, 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 and then a little square. That would be the Big Dipper. Right? It's the Big Dipper that we can see in the sun, in the sky right there. So what we want to do to continue to set this up is it says we want to enable the constellations and as well to the label. So in order to enable the constellations, remember you would come over here to View. We drop down to Constellations, and this time what we're going to do is we're going to just put on Astronomical so that we see the sticks for the constellations. And we can see here that Arcturus is in this constellation here. I think that's Bootes or Bouteille. And look, now you can really see the Big Dipper or the Great Bear, how the Great Bear, it's more than just the Dipper that we normally take a look at. It really does trace out a Great Bear there. Now, now we also they ask us to do labels. Now, so you can come up here to labels, and if you show all labels, it gets pretty messy. But at least it's doable. Okay. If you just want to see, and it didn't say, but if you just want to see the stars, you can uncheck the planets, the comets, the satellites, and so on. Okay, so now we've got this set up the way that they want us to, and the first star that we're going to look at here is Alpha Centauri. Now, this program is quite a bit different than the previous program in the way that it works. So let me show you. You come up here into the search bar on the control, you go up here to the search area on the control panel, and you type in alpha space cen, and you can see that you don't even have to type all of it in. It'll pop up with a couple of the only two objects in the sky that begin that way, and we want Alpha Centauri. Excuse me. I guess I'm a little sleepy today. You check on Alpha Centauri. Then there's a drop-down menu. You click on that drop-down menu and you hit Center. And another window will pop up, and it says Alpha Centauri is not currently visible from your location. Do you want to hide the horizon before centering? And the answer is yes. You want to actually see where Alpha Centauri is. At this time of day, at my location, Alpha Centauri has set. And so what we want to do is hide the horizon, and when that happens, if you hit spacebar, it'll go there immediately. So you can see that there's a lot of labels here, but Alpha Centauri is shown in the middle, and the little I button is the information button. So if you scroll over that little I and click I, the information for Alpha Centauri and for any center object will show up. All right, you write down the time and date that you are performing this observation. The azimuth and altitude, if you go to the directions or to the data sheet, you will see that you have a text box or a data box that you need to fill in. The data that you're looking for is azimuth, altitude, what constellation the star is in, the Bayer designation, and that represents that the Bayer designation represents the brightness that how bright a star is within the constellation. So the brightest star in the constellation is Alpha, the second is Beta, and so on. The distance from the Sun, the radius, temperature, apparent magnitude, absolute magnitude, and luminosity. So the first thing we want to do is find the azimuth and altitude. So we come over here and click on Position in the Sky. Scrolling down here, we can see that the azimuth is 210 degrees, 59.240 minutes. And the altitude is minus 30 degrees, 30.680 minutes. Now the minus 30 degrees on altitude means it's below the horizon by 30 degrees. So that was our altitude and azimuth. In constellation, we come up to constellation, we see it's in Centaurus. And the Bayer designation is not on this screen. So you go back over to General Info. It's not in General Info. Don't see it in Description. So I'm going to go to Other Data. Well, maybe it was in Position in Sky. Position in Space. General Info. There it is. I'm sorry. It was in General Info like I thought it was. I just missed it. Bayer is Alpha. It's the brightest star in Centaurus. So if you come right down here, you can see that's the Bayer designation. the distance from the sun, okay, and now that's the position in space. So we click on position in space, and we see the distance from the sun is 4 light years. The radius, it's neither position nor general, so you go to other data, and you can see that the radius is 1.4 times the size of the sun. It's bigger than the sun. The apparent magnitude, remember the apparent magnitude is the magnitude that we see. In other words, it's the relative brightness as seen from Earth. That's the apparent magnitude, and it's minus 0.04. So it's pretty close to Earth. It's only it's pretty close to Earth, only 4 light years from Earth, and so it's pretty bright. The negative sign on a magnitude means that it's bright. The greater the magnitude, the dimmer the star. Think of it in terms of race. First place is best, right? So first place is brightest, and that's how they initially ranked it. So as time went on, there was an initial ranking, and that started with 1. And stars that were brighter than the 1 star became a negative, right? It's in your book. The absolute magnitude is 4.31. That's a visual. And the luminosity, it's 1.8 times as luminous as the sun. So it's 1.8 times as luminous as the sun. That basically means that the amount of energy that it's releasing per square meter is about 1.8 times what it is on the sun. Okay, and that's it. We're done. Okay, so the rest of the stars, you'll do exactly the same way, right? You'll go up to the search, type in their name. Say Betelgeuse, B-E-T-E, right? Betelgeuse, so there's Betelgeuse there. Select it, drop it down, center, hit spacebar, then hit the information button, and you're there. And then you look around for the data, right? So it's pretty straightforward. And you'll also have to pick 3 of your own stars to take a look at, and pretty much that's it. That will be it. Now there are 2 other sections in the lab which are a little difficult for some people. If you go to the very back of your instructions, you will see on page basically 102 that there is a table here, and you're asked to determine the multiple of Alpha Centauri's brightness compared to these conditions, okay? Well, you have to, it's in the text, but it's kind of buried in the text, and I know that there's a lot of detail in there, but brightness of a star, the way we perceive a star, the brightness, is proportional to the following. It's proportional to the inverse square of the distance. What that means is that if a star is further away from Earth than Alpha Centauri, say it's twice as far away, then it's going to be 1/4 the brightness, because stars get dimmer the further away they are from us. They appear to be dimmer the further away they are from us. And brightness is really just apparent magnitude. Now, because brightness has to do with the amount of energy being released from the surface of the star, then the brightness is proportional to the 4th power of temperature. And we studied that, Ryan's law, earlier in the text. So the amount of energy released by an object is proportional to the 4th power of temperature. The hotter it is, if it's twice as hot then it's 16 times as bright. Now remember that the temperature has to be in Kelvin for this to work. And brightness will always also be, an object will also be brighter if it's bigger, if it's the size of it is larger. This is because it's proportional to the square of the radius, because area is proportional to the square of radius. The area of a circle is pi r squared. And stars are spherical, and so the surface area of a sphere is proportional to, it's 4 pi r squared, I believe the area of a sphere is. And for some reason, I'm not sure why, but I'm blanking on that. Let's just do that area of a sphere to make sure. I am not steering you to right. 4 pi r squared exactly is the area of a sphere. So I did remember that. It's good that I did, right? The point of it is that when a star gets larger, there's more surface area to emit light, and so the star is brighter. And let me just do a couple of examples to show you how this works. Consider two stars, A and B. If they are both the same size and temperature, but star B is 4 times farther away than star A, how much dimmer is star B than A? All right, so let's just take a look at this, all right? So we know then that the factor that we're going to be looking at is, since the temperature, basically brightness, is going to be, the relative brightness will be equal to 1 over the distance squared, and I'll use capital D because it's easier for me to write with a pen, times the temperature to the 4th power times the size or radius squared. So we'll go size squared. Now in this case, the temperature and the size are the same for both stars, so that means that the one is not bigger than the other. It's just that it's the same, right? So we'll use 1 for that temperature. And basically, this comes about because we're thinking about ratios here. And I guess I could show you, but just do it this way. So the distance is 4 times bigger, and so now the distance is 4 times larger. And it'll be squared because the distance is 4 times larger. The temperatures are the same, so the differences are going to be just times 1 and times 1 again squared. So the brightness, the brightness factor between these two is that star B will be 1/16 the brightness of star A. And I can show you kind of how this works if we do a new page. Basically, what we have is we have that the brightness of an object is equal to some constant times 1 over its distance squared times its temperature to the 4th power times its size squared. So that's be like for star 1, right? And these are all 1s here. And brightness of star 2 is equal to the same thing. It'll have the same constant in it, 1 over the distance 2 squared times the temperature 4th squared times the size for number 2 squared. That's not square there. And what you're doing is you're figuring how many more times is star B, what's the brightness, how many more times, or what's the factor between the brightness of star 1 compared to star 2. So what you do is you'll do the brightness of 1 compared to the brightness of 2. All right? So when you divide those two formulas, the k's drop out, and we will look at 1 over d1 squared times t1 to the 4th times s1 squared all over 1 over d2 squared times t2 times s1 squared. Now, if the temperature and the size are the same, these will cancel, right? Because they're the same numbers. And then it just comes down to 1 over d1 divided by 1 over d2. Okay, but now we said that in this example we said that the distance from to star B to the first star or to the second star was twice the distance of the one we're comparing it to. And I know my subscripts are a little weird, but so we said that it was 4 times further. So that means that D1 is equal to 4 times the distance to D2, is what we said, right? So if you substitute this in, and by the way, if we just rearrange this, if we rearrange this by inverting and multiplying the denominator, you're going to get D2 all over D1. Now, since D1 was 4 times further than D2, we can substitute that in here. We'll have D2 squared. Down here, it will be 4 times D2. We're just substituting in, and the whole thing is squared. Okay? So now what happens is that the D2 squareds cancel, and you're left with 1 all over 4 squared. All right? That's what you're actually doing, and but instead of going through this process every time, all we really have to remember is, and we'll go back, is that the brightness, the relative brightness is just 1 over the distance squared times the temperature to the 4th times the size squared. The temperature to the 4th and size squared, I could show that, using the cancellation, the ratio, that this is going to work, okay? So in the, if the brightness then oops. If we take a look, it looks like this is too far down there. I'm going to move this up so that we can see if we can't do that. Okay, consider 2 stars, A and B, if they both have the same distance and size, but star B is 4 times warmer than star A. How much brighter is star B than star A? Okay, the brightness, the relative brightness is going to be equal to, since the distance and the size are the same, all we have to consider is the temperature, and the relative brightness between the two is to the temperature to the fourth power. So this means that since it's 4 times warmer, it'll be 4 to the fourth, and I need a calculator for that. And I'll clear. You guys probably have already done it. Oh, there it is. 4 to the fourth power. For x to the y to the fourth power equals 256 times. It's 256 times brighter. And again, it's because that the temperature is 4 times brighter. The amount of energy that's emitted from an object depends on the fourth power of temperature, not just the temperature itself. So here, this bright, so star B is 256 times brighter than star A because it's 4 times warmer, 4 times as hot. Again, this has to be Kelvin. So it's not that you go from 100 degrees Celsius to 400 degrees Celsius. You have to go to Kelvin. You have to increase it by Kelvin, and so remember that to change from Celsius to Kelvin, you add 273. So 100 degrees Celsius is equal to 373 Kelvin. All right. So this is going to be 373 times 4. That would give you 1,492 is 4 times as bright. And okay, it's 4 times as bright. 1,492 is 4 times as bright. At any rate, so what we've got then here is we have an example from the book, and let's do an example from the book. Basically what it says is, if you take a look at the first example, the star that we're comparing to is Alpha Centauri, and our hypothetical star has twice the distance, it's the same temperature, and it's twice the size. So the brightness, the relative brightness, is going to be twice the distance. So remember, it's distance over, it's the inverse square law for the distance. It's distance squared one divided by the distance squared. Okay. Now the temperature is the same, so we can leave that out, but we do have to multiply by the size, and the size is going to be twice the size. So the size is squared, remember, because it goes as the square of the radius. The area increases as the square of the radius. And so here in this case, we get 4 over 4. The two stars are equally bright. So our hypothetical star is as bright as Alpha Centauri. So that's the quantitative. This is quantitative. That's the quantitative value. The qualitative value is that they are the same brightness. And that's the qualitative description. Okay? So on your data sheet, you have to do both. So if the star is brighter, then you would say that for the qualitative thing, you would say it was brighter. For and you could give it as how many times brighter. So suppose it was 16 times brighter, you could say it's 16 times brighter. Or 1/16 as bright, you could say 1/16 as bright, or you could say just dimmer, it's dimmer, the qualitative. Quantitative, you'll have a number for each of those. Let's do one more here. It says it's twice the distance, twice the temperature, and twice the size. So remember, if we take a look, remember our brightness formula, it's proportional to 1 over the distance squared times the temperature to the 4th, the relative temperature to the 4th, times the size squared. And in this case, we'll have 1 over 2 squared times 2 to the 4th, because it's twice as hot, times it's twice the radius, twice the size, so it's 2 squared. These cancel, and we're just left 2 to the 4th, which is equal to 16. So it's 16 times brighter, and the qualitative is that it's brighter. Okay. Now the very end, the very last thing is lots and lots of stars. It says that what we want to do is how many years would be needed to count the stars if there are 200 billion stars in the Milky Way and we counted 1 a second. 24 hours a day, no breaks. How long would it take? Okay, so we have 200 billion stars. That's 200, and a billion is times 10 to the 9th. That's the number of stars we have. Okay, so if it takes us 1 second to count these stars, then we can multiply that by 1 second per star, right? That's how long it takes us to count. All right, the stars cancel, and we're left with 200 times 10, 200 billion seconds is how long it's going to take us to count that. Now the question is, how many seconds are in a year? So we know that we have 1 year is equal to, what is it, 362 days? Times 24 hours in a day times 60 minutes per hour times 60 seconds per minute. That'll give us how many minutes there are. This is hours per day, minutes per hour, and seconds per minute. So my hours cancel, my days cancel, my minutes cancel, I'm just left with seconds, okay? So that, all you got to do is you calculate that up, and that's not 362, it's 365 days a year. So I messed that up, 365 days per year. Don't know what's happening with me today. So we take 365 times 24 times 60 times 60 again, and you'll come up with some number. I came up with 31,500,000 36,000 seconds in 1 year. All right? So now what we do is we know that that's how many seconds it is in a year. So how many years will it be? Well, we have to convert seconds to years. So we'll have 200 times 10 to the 9th seconds times 1 year per 31,536,000 seconds. Now, when you convert here, see, we wanted it in years, so we had to put the year on top, so when we multiplied it, they would cancel. So here my seconds cancel, and I'm just going to divide 200 times 10 to the 9th by 31,536. So if I grab this out, grab a calculator, 200 e to the 9, divide by 31526,000, and it gives me like 6,344 years, okay? So 6,344 years is how long it would take if I counted the stars in the Milky Way galaxy, and it took me 1 second to do it, and I never stopped. So that's how many stars there are up there. That's how many stars 200 billion stars is. Okay. So there's another calculation there for the Andromeda Galaxy. You can work through that same process that I just did, and that should help you out. So that's it for observation 3, activity number 19. If you have any questions, please let me know. I will post this for you to read, to view. Thank you.